This time in lab, we're going to be talking about binary arithmetic circuits. These are the circuits that allow you to do addition and subtraction in particular. There are different circuits that allow you to do multiplication, but addition and subtraction are really central to an awful lot of the work that we're going to do. So we're going to talk about how to do this, how to build an 8-bit adder from 2 dip switches, 2 4-bit adder chips, and a bar LED. We'll be able to plug numbers into the dip switches, have the calculation be performed, and observe the result on the bar LED. So we're going to verify that it performs the addition correctly and verify that it can actually be used to do subtraction as well, because we're going to negate the second number using 2's complement arithmetic. So don't forget this lab has a pre-lab. We'll get to that in here in just a second. We already studied the full adder and the half adder circuit. We understand the sort of differences between them. The half adder just adds 2 1-bit numbers. The full adder adds 2 1-bit numbers and a carry in. But the carry in is just as significant as the 2 1-bit numbers, so it's really adding 3 1-bit numbers. In both cases, it's going to generate a sum and a carry out. And so really it's the full adder that we're going to spend most of our time talking about. And the full adder is essential because it can be used to string several of these circuits together to generate a multi-bit adder. And so that's what you can see here, is that if you have the carry in from every bit is coming from the carry out of the next least significant bit, then you can actually string these together. It's called a ripple carry. And ripple carry is easy, it's nice, and of course that's the first thing that we should learn. As you move forward, you'll understand that ripple carry is also pretty slow. And so there are other techniques that you can use, known as carry look ahead or fast carry, that can be used to perform these calculations more quickly. So for the future, again, something for your sophomore year, but for now, we can do 4-bit full adders, we could do 8-bit full adders just by stringing them together as well. Here you can see that a 4-bit full adder is actually available as its own discrete chip. And so you can see there's 2 4-bit numbers on the top, there's a 4-bit sum on the bottom, there's a carry in, and there's a carry out. And so this actually, we got 4, 8, 12, 13, 14 pins plus a ground plus a power, that's 16 pins. That's just about as compact as a chip can be. It's got an awful lot going on there with just 16 pins. It's one of sort of the most beneficial 7400 chips. So we can actually take 2 of those together. We can take 2 of these 4-bit adders, taking the carry out of the least significant one and sending it into the carry in of a second, more significant full adder chip. And what we end up with is an 8-bit adder. Now the 8-bit adder is really nice because it can bring in 2 8-bit numbers, and those 2 8-bit numbers are added together to yield an 8-bit number and a carry out. You can kind of think of this as like the 9th bit, because that 9th bit is going to give you the capability of going to a number that's higher than 255. If you think about it, this 8-bit number here can represent anything up to 255. This number can represent anything up to 255. So the result could be as high as 510. And 510 will not fit into these 8 bits right here. You would need a 9th bit. With the 9th bit, you can go as high as 511. So certainly we can represent 510 with 9 bits. So this is the ultimate goal. This circuit is what we're trying to build, and we're going to do that by combining together 2 74 LS83 circuits. 74 LS83 chips. And so here we have really the central figure of the entire lab. This is where you're going to be, this will be the circuit that you're going to construct. So we have 2 74 LS83 chips. I've referred to this one as being for the most significant bits, and this one is for the least significant bits. And so you can see that I have pins B0 to B3, or signals B0 to B3, and signals A0 to A3. Those are going into the left, or the right, or the least significant bit chip. And then it's going to generate 4 sum bits as well. Notice that we don't have a carry in. The carry in is just grounded here because this is the least significant bit, least significant bits. And then the carry out from that calculation is going into the carry in of the most significant bits chip, where we get A7 to A4 and B7 to B4, and we generate S7, sum 7, down to sum 4, and we have the carry out, which is on pin 14. So we're gonna send these 8 bits of the sum to a bar LED, and we're gonna send the carryout to just a single LED. I wanted to separate the carryout because sometimes the carryout is important and sometimes the carryout is not important. For our purposes, for the calculations you'll be doing, you should consider the carryout for addition and you should not consider the carryout for subtraction. But it's a bit more complicated than that. There's a thing called an overflow detector that you're going to learn about next year when you study these circuits again. For now, though, just know that the carryout is useful for addition and it's not useful for our subtraction calculations. Now, before you actually build that circuit in lab, we need to know what would be some good verification tests. And so I'd like you to do some pre-lab calculations, converting the number 76 into binary and the number 44 into binary, then performing the binary addition of 76 plus 44. Notice that this is a bit wider on the sum because there could be a 9th bit coming out here. It'll be 0 for this particular one, but it could be 1 otherwise. So you'll do this calculation bit by bit, showing the carry up here. So if you have a carry between 2 bits, I'd like you to show that up here so that you can see how the carry out works from 1 bit to the next. Then take this number and convert it back into decimal, and then that result will go right here, and then verify that that in fact is the correct sum if you were to add 76 plus 44. Over here you can add 225 to 150, and again you'll convert 225 into binary and 150 into binary. Do the bit by bit addition with the carryouts, and this one might not be 0, and then convert this number back into decimal and verify that you get the correct answer, 375. So those are the first 2 sample calculations. Then the next ones are going to involve some negative numbers. So I'd like you to go ahead and calculate these separately so you don't have to worry about them while you're in the middle of the addition or subtraction. So figure out what is 30 in base 10 if you convert that into binary. And then remember that to represent that as 2's complement, you would simply invert every bit of this number and add 1 to the result. So that's how you'll find negative 30 in base 2. And then do the same for 110 to get negative 110, and for 33 to get negative 33. So in each case, you'll do a conversion from decimal to binary, and then you'll do a 2's complement by inverting every bit and adding 1 to find the negative version of that number. Once you've found negative 30, negative 110, well, the negative 30 goes right here, and the negative 110 goes right here, and you can figure out 100 in binary and 77 in binary. And then do the addition, because since we've accounted for the negative sign by converting these to 2's complement, we're doing not 100 minus 30, we're technically doing 100 plus negative 30, and 77 plus negative 110. So now we just do addition again. You don't need to do subtraction, you just do addition bit by bit, and as you do the addition, fill in the number down here. Again, you can ignore the carry out of the most significant bit. So what you're looking at is just the 8 bits that you're going to get in this addition, and then that you'll either get a positive or a negative number, convert that into a decimal result, and verify that it's the correct result for over here. And by the way, 77 minus 110 is negative 33. So that's why we did the negative 33 here, was so that when you get this answer, it should match this box right here. And if it does, then you've done the calculation correctly, because this should be negative 33. So your goal in this experiment is to actually construct the circuit from figure number 6. So some helpful hints: remember to take the inputs from between the dip switches and the resistors. Anytime you have a switch and a resistor, that's where you take the input from. The outputs go to the top of the LED bar so that they pass through the LEDs and through the resistors on their way to ground. A7 and B7 are the most significant bits. Those are on the left of their respective dip switches. A is on the left. A is the left dip switch and B is the right dip switch. And A0 and B0 are the least significant bits. We usually use 0 to represent the bit number of the least significant bit, and in this case, since there are 8 bits, it goes all the way up to A7 and B7. You should never need to connect 2 wires to the same pin in this circuit. This was actually very helpful to me as I was building this circuit. There were a couple of times that I almost made a mistake, and then I realized, oh no, there's already a wire in that pin. So just realize that as you're plugging each wire in, you should never find that you're plugging it into the same pin as a previous wire. And if you have, then one of those 2 wires, or possibly both of them, are wrong. The chip labeled 74LS3 LSB, so let me flip back up to figure 6. This is 74LS83 MSB is going to be the chip on the left, and 74LS83 LSB is the chip on the right. So when you get to lab, there'll be a chip on the left and there'll be a chip on the right. Remember that the MSB chip is on the left and the LSB chip is on the right. And then the most common mistake would be to forget to connect the carry out of the least significant bit chip to the carry in of the most significant bit chip. That connection has not been made for you, so you'll have to make that connection with a jumper wire. You'll have to connect eight jumper wires for input A, 8 jumper wires for input B, 8 jumper wires for the sum going to the bar LED. That's 24 total. Then a 25th jumper wire to connect the carry out to the carry in. That's 25. And then you're going to need to connect the carry out of the most significant bit chip to a single LED. So I think you're going to need 26 jumper wires. It might be that both you and your partner will need to bring your jumper wires to lab tomorrow. So double check your connections, and my advice would be before you turn on the power, make sure that it's preset to 5 volts. That's what the power connection should be this time. And then when you turn on the power, just real quick, double check to make sure that the current isn't too high. If the current is more than about 0.1 amp, or if the overload light is on, then that means that you've made a connection that's wrong. And if you leave that connection on for more than a couple of seconds, you're probably going to overheat and destroy the chip. But if you turn it on, see that it's wrong, and turn it off immediately, then you probably won't damage the chip. So in a circuit like this where you've got 26 or more wires to connect, I always kind of am ready to turn on the power. I turn it on, check to see if everything looks good, and if it does, then I leave it on. But if it doesn't, then I turn it off immediately because I know that I need to double check something again. So to verify your circuit, enter each of the 4 addition and subtraction problems from the pre-lab. Verify that you get the same results for each of them as you did when you did them by hand. And when you've successfully achieved all 4 of those results, please just come to get the professor or the lab assistant and demonstrate it to us, and you'll be good to go.